everyone, I am Dr. Jagadha, Associate Professor in the Department of Mathematics. We will discuss about the topic problems on infinite Fourier transforms. In detail, we will talk about definition of infinite Fourier transforms, problems based on infinite Fourier transforms. The function f of x, which is defined in an infinite interval, that is, x lies between minus infinity to infinity. If this interval exists, then we will call such a Fourier transform as infinite Fourier transform. Problems. Find the Fourier cosine transform of f of x equal to 1 by 1 plus x square, and hence find the Fourier sine transform of f of x equal to x by 1 plus x square. So the first one is the Fourier cosine transform of f of x equal to the function which is given as 1 by 1 plus x square. So this first part, first we will concentrate for the solution. So for which we selected the formula, the Fourier cosine transform formula. Here in this, they didn't mention anything, whether it is function only it is given. There is no range, that is the interval x lies between from where to where, it is not at all mentioned. If it is mentioned minus infinity to infinity, then we will select infinite Fourier transform. But without here finite it is not mentioned, infinite it is not mentioned, then if it is not mentioned, only the function it is given, by default we can select infinite Fourier transform. So we selected the infinite Fourier transform for the cosine. It is capital FC of the function f of x. That is Fourier cosine transform of the function f of x equal to capital FC of p equal to integral 0 to infinity f of x cos px dx. So easy way to remember, if it is Fourier cosine, the trigonometric term cos will be dominating in the formula 0 to infinity. If it is not mentioned, infinite Fourier cosine also, by default nothing is mentioned, that is the interval about no information is given, then we will select by default infinite. So we selected the infinite Fourier cosine transform. Now, the f of x we have to replace by our function 1 by 1 plus x square. So we replaced, that is, our f of x as 1 by 1 plus x square into cos px dx. Integral 0 to infinity. That we have given a name capital I. So that is a simplified form which is given here, cos px by 1 plus x square dx. It is named as 1. We are going to do differentiating, that is, capital I equal to integral 0 to infinity cos px by 1 plus x square dx. This both the sides we are going to do a differentiation with respect to p we are going to do. So if you do the differentiation, this left side, the I, it is becoming di by dp, which is equal to d by dp fc of f of x. So it's nothing but the Fourier cosine of the function f of x. So with respect to p, we are going to do. So if we do this with respect to p, the differentiation is, so where the term is there, here the p is occurring. So remaining all in terms of x, our aim is to do the differentiation with respect to p. So cos px is there, that is, cos the differentiation is minus sine. So here minus sine px. So the p coefficient we want it. So the p coefficient, we have to leave p. The remaining is x. So this is differentiation. The coefficient should be written under multiplication, that is x into sine px divided by 1 plus x square dx. This we will limit as equation 2. So now, so the equation 2, we are going to do multiply and divide both the sides by, that is up and down, we are going to multiply by x. Mathematically it is correct. So the upper one already x is there, x into x, it is becoming x square sine px divided by x of 1 plus x square dx. Now everything we have written as it is. Here this term everything, only the change we brought in here, that is add and subtract 1 we did. So many assumptions we are introducing while solving the problem. First here, multiply, that is both the numerator and denominator by x we did. The next, add and subtract the number 1 we did now. So now this 1 and x square put together, it is going to become as one term. So 1 plus x square divided by x of 1 plus x square. We can write it. So this getting cancelled, balance 1 by x. So we selected in this 1 and x square already put together. This change it has come. So the remaining is minus 1. That we will write it minus 1 by exactly the denominator, what it is there, we presented here, into sine px dx. Now, this as one integral, this as another integral. So we are going to split the one integral as two integrals we are going to write. So it is written here, minus integral 0 to infinity sine px by x dx plus integral 0 to infinity sine px by x of 1 plus x square dx. So this integral, the value is pi by 2. So minus pi by 2 plus this as it is we have written, we didn't bring any changes. That is 0 to infinity sine px by x of 1 plus x square dx. This is only our question, that is our f of x is this one. Fourier cosine of the function f of x, that only we are concentrating now. Now, we did the differentiation with respect to p and we got this result. Here we put it once again. Why these steps once again we are recollecting? The reason is we are going to do this. This is our question. This is our function. For the function we are asked to Fourier cosine. That we did the first time derivative. We got this result. That is this one. This once again we are going to do the differentiation. That is, this we are going to do the differentiation again with respect to p. So again, if you do the differentiation, this is constant. We know it. The differentiation of constant is 0. So this term completely it is getting vanished. So it has become 0. So the next one is integral 0 to infinity sine px by x of 1 plus x square dx. Where p is there, only the numerator part, the term, the trigonometry, sine px is having the letter, the variable p is there. So sine px, the differentiation is, we know it, cos px. Again, the coefficient of p is x. That is, we will leave p, the remaining will become as coefficient. That we have to write it under the operation multiplication divided by the exactly what is the numerator, we will write it. This getting cancelled. So this particular thing, entire thing, it is replaced by cos px divided by 1 plus x square. So we are getting, this is our question, what we have to do it. That first time we did the differentiation, this is the result we got it. This once again, now we explained the differentiation for the second derivative. We got it 0 to infinity cos px by 1 plus x square. So the second derivative, it's nothing but we are going back to our question. So this is the second term derivative which is equal to fc of f of x. Now, so the 2 times derivative d square by dp square fc of f of x equal to integral 0 to infinity cos px by 1 plus x square dx. So the complete thing, it's nothing but the starting. What is the question? We did fc of f of x is coming back again. That we noticed it here. So the 2 times derivative, it's nothing but fc of f of x. It should not be there here. fc of f of x. Now, this, we got one differential equation. The main reason, the starting multiply both the numerator and denominator by x, one assumption we did. Add and subtract, one assumption we did. These two assumptions we did. The reason is we want the given integration in terms of one differential equation we want it. That is the reason those assumptions we have taken earlier, that we discussed also just now. Now, this differential equation in terms of, that is very simple way we can say, that is y double dash plus 3y dash plus 2y equal to, if it is there, this differential equation we know it 3d plus 2 of y equal to 0. It's a small differential equation. We will find auxiliary equation, complementary function, then general solution, we will find it. That is in terms of y we are habituated. Here we are doing Fourier cosine. That is the differential equation in terms of our fc of f of x. So 2 times differentiation is there. That is the reason here d square. This fc of f of x we are bringing to the next side. That is from right to left we are bringing. So it is becoming minus in terms of the equation which is defined in terms of fc of f of x. Fine. So d square minus 1 of fc of f of x equal to 0, for which we have to write the auxiliary equation. So the auxiliary equation is d square we are taking as m square minus 1 equal to 0. So m square equal to 1, m equal to square root of 1. It's nothing but plus or minus 1. So plus 1 minus 1. Two values we have to get, we have to get. The reason our differential equation, the order is 2. If the order is 2, we have to get 2 values depending on that. So we got it. The one value is plus 1, another one is minus 1. This plus 1, we will name it as m1. The next minus 1, we will name it as m2. So the general solution is, for which this is c1 e power m1x plus c2 e power m2x. This is the, in terms of general, that is a differential equation, we will be the formula for the general solution. But whereas ours is, which is defined in terms of fc of f of x, and we did the differentiation with respect to p we did. So our x is, in general x we are habituated. We did so many in the lower classes those problems. Here we did the Fourier cosine transform equation. How we got it? We did the differentiation with respect to p we did, and we got the equation. So in terms of x, ours is p. So c1 e power m1 into p plus c2 e power m2 into p. So fc of f of x equal to c1 e power m1. So our m1 is plus 1, m1 p, that is 1 into p, it is written e power p. In this place, m2p, our m2 is minus 1. So minus 1 into p. So c1 e power p plus c2 e power minus p. This is the general solution we got it for our differential equation in terms of Fourier cosine of the function f of x. That we named it as equation 3. So, we are going to now the equation 1. This is our equation 1, that is fc of f of x, Fourier cosine transform of the function f of x, which is equal to integral 0 to infinity cos px by 1 plus x square dx, and we named it as 1, in which we are going to substitute our p equal to 0. So this again we wrote it. In this we are going to substitute. This we solved the differential equation in terms of fc of f of x, that is c1 e power p plus c2 e power minus p equal to, this is our right hand side. Now we will do the comparison of this and this. The p place we substituted 0, so the totally it is becoming cos 0, so the value is 1. So 1 by 1 plus x square dx. The similar manner, the same way, we will substitute in the left hand side where p is there, we will substitute 0. We know it here, e power 0, the value is 1. Here also, the value is 1. So c1 plus c2 equal to, this integral is tan inverse x 0 to infinity. So we got it c1 plus c2 equal to pi by 2. So we have taken our equation 1, in which we substituted the value p equal to 0. We got c1 plus c2 equal to pi by 2. Why we have to do all these steps? The reason is, we got the general solution of Fourier cosine transform as c1 e power p plus c2 e power minus p. Those constants c1 and c2, the values we have to obtain. To obtain those values, these are the steps we are following. Now, we will substitute in equation 2. So, for which, what is this equation 2 which is written here? We are going to use equation 3, help we are going to take. For that, d by dp of, this is Fourier cosine of the function f of x. So that is the, we were just now, the differential, the general solution of Fourier cosine transform of the function we did, that is substituted here. This minus pi by 2 is as it is. This we didn't touch it all, just without any changes, it is written here. So this is the last step of the previous slide, from which this how we obtained, that is with the help of equation 2 and equation 3, this is written. Here we are going to substitute p value as 0. So if we substitute here, first we will do this differentiation with respect to p. So if we do the differentiation with respect to p, c1 e power p plus, but c2 here e power minus p is there. We know e power minus x, the differentiation is minus e power minus x is the differentiation of this one. So in this way, here minus e power minus p is coming. So we got c1 e power p minus c2 e power minus p, which is equal to this side minus pi by 2. This side p is there. In the p place we are substituting 0. So sine 0, 0, the totally this integral is getting vanished. Whereas left hand side, after doing this differentiation with respect to p, we obtained c1 e power p minus c2 e power minus p, we got it, in which we will substitute wherever p, the value 0 we will substitute. So e power 0, the value is 1. So it is becoming 1. This is also becoming 1. So after the substitution, we obtained the result c1 minus c2 equal to minus pi by 2. Now solving, our aim is what we obtained our general solution c1 e power p plus c2 e power minus p. In that we want to know the value of the constants. To find the value of the constant c1, c2, these are the steps we are doing. First, the equation 1, we substituted the value p equal to 0, we obtained c1 plus c2 equal to pi by 2. And equation 2, with the help of equation 3, we substituted p equal to 0, we obtained c1 minus c2, which is equal to minus pi by 2. So now these two we have to solve. Very easy way, they are getting cancelled, and this is also cancelled if we add these two. So 2c1 equal to 0 we are getting. So c1 equal to 0. So 2c1 equal to 0, from which we obtained c1 equal to 0. So the out of the two constants, c1 result is obtained. With the help of c1, any one of the equation, if we substitute c2, we will be getting. So if we substitute in this place, so we are getting, this is after substitution, c1 is vanished. So c2 equal to pi by 2. So it's very clear here. So what we discussed, it is written here. c2 equal to pi by 2. So our general solution of our Fourier cosine transform of the function f of x is c1 e power p plus c2 e power minus p. Fine. So the Fourier cosine of the function f of x equal to, this already, the c1, the constant, we obtained the result as 0. c2 we got it pi by 2. that is substituted here. So I equal to pi by 2 e power minus p. So the first part of the problem, find Fourier cosine transform of the function f of x equal to 1 by 1 plus x square. This is the first part of our problem that we solved. This is the result we got it. Whereas the same problem, second part it is there. The second part is nothing but find the Fourier sine transform of f of x equal to x by 1 plus x square. The second part is so we can take this with the second part, the first part how we did. The similar manner we can do it, we can achieve the result. But what we are going to do, we are not going to do the same way. With the help of the first result, is there any possibility we can, in a very easy way to solve this, the second part, we are going to do in such a way. That is, the first result, this is related to our Fourier cosine transform. The Fourier cosine transform, what is the result we achieved? That we are going to do differentiating with respect to p. So, this differentiating with respect to p, so we are writing d by dp of our Fourier cosine of the function f of x, which is equal to, this pi by 2 is written as it is pi by 2. This e power minus p is there. That we can write it as, we know it, e power minus x differentiation minus e power minus x. That is usually in general, that is e power x. If our complete problem in terms of p, we are doing differentiation, the entire problem with respect to p we are doing. So e power minus p, the differentiation is minus e power minus p. That minus only this one. So minus pi by 2 e power minus p. So now this fc of f of x, the initially starting only, that we have given, we named it as I. So di by dp equal to the same without changes, we have done it. So this is the second equation, the starting of the problem, what we got it, that just now we got it di by dp equal to minus pi by 2 e power minus p. So both the left sides equal. So we can equate the right side the terms. So we are equating the right side terms. Here minus, this side also minus is there. So both are getting cancelled. So after getting cancelled, the negative sign, x sin px by 1 plus x square dx equal to pi by 2 e power minus p. Where actually we are moving to this problem for the solution? Actually, our aim is find Fourier sine transform for the function x by 1 plus x square. This is only our second part question. If it is Fourier sine transform, the formula it is the 0 to infinity f of x sin px dx. This is the formula. But we don't want to do. The first part, Fourier cosine, we did the similar manner. But the second part, instead of going this formula, we are skipping entirely these steps, skipping what we obtained the result from the Fourier cosine. With that Fourier cosine help taking, we are going to find Fourier sine of the function x by 1 plus x square. That is a small trick. What we obtained the left side, it's nothing but, if you are noticing, this is the Fourier sine transform formula. That is 0 to infinity f of x sine px dx. This is our Fourier sine transform formula. If you are noticing exactly our left side, it is fit to our this formula. That is sine px, it is there, yes, dx it is there, and 0 to infinity it is there. The left is x by 1 plus x square. This is exactly, it fits to the second part of the problem. What is f of x? So, this in a simplified format, we can write it, that is Fourier sine transform of the function f of x, we can write in this format. In this f of x is playing the role x by 1 plus x square. Such a beautiful problem this is. So, Fourier sine transform of the function f of x equal to pi by 2 e power minus p. So, that's what it is given. This is our f of x. So, completely, this is f of x. This is sine px, integral 0 to infinity dx. So, entire thing, it is fit for capital F, our Fourier, capital F, yes, that is Fourier sine transform of the function, our f of x, that is x by 1 plus x square. The value is pi by 2 e power minus p. So, instead of doing the long way from the first part of the solution, with that help, we derived the second part of the problem. So, here it is very clearly, it is mentioned, Fourier sine of f of x, which is equal to pi by 2 e power minus p. So the first problem we concentrated in detail. The second one is find Fourier cosine transform of f of x, defined by f of x equal to x. That is, the function is x. If x lies between 0 to 1, take the function that is x. If x lies between 1 to 2, here 1 should there. If it is 1 to 2, then the function is 2 minus x. If x is greater than 2, that is, it starts from 2 to goes on, that is up to infinity. Up to infinity. So the starting is 0, ending is infinity. 0 to infinity. That is our interval range. The length of the interval 0 to infinity. We know it, our Fourier cosine transform formula is integral 0 to infinity f of x cos px dx. But the 0 to infinity is splitted in such a way. The first one is 0 to 1, next 1 to 2, next 2 to infinity. So the 0 to infinity 1 integral is splitted in such a way as 3 integrals. That we will concentrate how we are going to solve using this Fourier cosine transform formula. So the Fourier cosine transform formula is capital FC of f of x equal to integral 0 to infinity f of x cos px dx. It should be here 1. So x lies between 0 to 1 and x lies between 1 to 2 and x is greater than 2. This is our equation. 0 to infinity f of x cos px dx is our Fourier cosine transform formula. So 0 to 1, next 1 to 2, and this is 2 to infinity. So that 0 to infinity, here it is there, it's a hiding one. 0 to here infinity is there, the top of it. Whether we are solving the problem, the direction, what we are doing, it is a correct path or not, we can cross-check ourselves. That is, 0 starting, the ending here is infinity. So we can cross-check it. Yeah, we inserted it is a correct way. Even the starting of the noticing, here the typing, the mistake it is there. In this place, 1 should come. I corrected myself because here 0 it is there. So see what we inserted, up, down, like that, the same format it should be there. The continuity of the interval should be there. Otherwise, we are doing a mistake. We can cross-check and we can correct where is the mistake and we have to proceed our problem. Now, the 3 integrals we have to concentrate. The first one is f of x cos px dx. Fine. This how to read? So x lies between 0 to 1, that is f of x is replaced by x. Here f of x is replaced by 2 minus x. Here f of x is replaced by 0. So we can see it here. So the f of x is replaced here x, and in this place f of x is replaced by 2 minus x. This is 0. Now x cos px, 2 minus x cos px, the third integral is getting vanished. Now the first integral is 0 to 1 x cos px dx plus integral 1 to 2 2 minus x cos px dx. So now the integration, that is the regarding Fourier sine transform. The first integral, the result which is given here. The second integral, the result is written here. The first integral, we know it, integral 0 to infinity x cos px dx. This result only it is written here. How we obtained this result? Very simple way. In this x cos px, X is algebraic oriented, cos px is trigonometric oriented. When the integration regarding algebraic and trigonometric, if it comes very easy way, the algebraic one, we will do the differentiation, that is x. Regarding x, the differentiation is 1. Again, the 1 differentiation is 0. Cos px integration is sin px divided by p, that is with respect to x we are doing. So the x coefficient is p, so divided by p. Again, this we have to do the integration. Sine integral is minus cos px divided by p, but already before the p exists, so p square. The next we have to continue, but in the differentiation side, 0 it is there, so we no need to continue. We will stop the procedure. This is very simple way of doing integration. So we can see, we can focus this into this. That's what here it is written. And these two multiplication is here it is written. So x, the differentiation is 1. Suppose if the problem continues, the next we will be going on, we will be doing the differentiation. It is to understand more, to understanding level, to enhance. It is blue color we shaded. The integrated one, it is shaded in red color. So our question, the first integral, x cos px, algebraic one, the part is in blue color, the differentiation. Trigonometric one, integrate, and we have to put it. The middle signs will be alternative signs, 0 to 1. This is our second integral, that is integral 2 minus x cos px dx. So the 2 minus x is algebraic, so it is written here. So the algebraic one we will be doing under differentiation. So the 2 differentiation is 0 minus x differentiation is 1. So here minus 1 it is there. So the differentiation part regarding we completed. Next we will move to the trigonometric term cos px. Integrate, and we have to put it. So the integrate one is sin px by p. Again, the integrated one, sin px. Sin integral is minus cos px divided by coefficient of x. Why we are not taking coefficient of p? We are taking coefficient of x. The reason is we are doing the integration with respect to x. So the coefficient of x we have to leave. The remaining is p. So that is becoming as coefficient. So divided by p, but already before the p exists, p into p, p square. So algebraic one, differentiation under trigonometric one, Under integration, middle sign, that is between the terms, alternative signs. Here the positivity is there. So default we know it. If plus, no need to write. The next is formula sign. Suppose if it continues the problem, we will write plus, minus, it goes on alternative signs. Now the upper limit is 2, the lower limit is 1. The next step, we have to apply the upper limits and lower limits. So here, before substituting the upper limit, that is 1, we have to make the terms. Here, the first term is there. Here, the second term is there. The terms should have a single sign. The simplifications to be done. To avoid, we no need to give room for committing mistakes. Completely we can avoid, we can escape from the careless mistakes. So that's what here x sin px by p minus into minus, it is plus cos px by p square 0 to 1. Next 2 minus x sin px by p. Here the single sign, 3 negative signs are there. So minus, 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 it has become minus cos px by p square from 1 to 2. So now we will apply the upper limit in the place of x. So here 1, 2 places. We substituted, we got it sin p by p, the same plus as it is. Here we substituted the upper limit in the place of x, 1 cos p by p square minus, this is the upper limit, the 1, the value substitution is over. Next, minus the lower limit. So the lower limit is 0. So if you substitute here in the place of x, 0 into anything, 0. This is formula minus. Here, x plus 0 substituting cos 0, the value is 1. So 1 by p square. So it has become minus 1 by p square. So completely the substitution of first integral is over. Next we will move to the second integral. That is, x place we will substitute the upper limit 2. So 2 minus 2, it has become 0. So it is vanished. So the result is 2 minus, here x is replaced by 2. So it has become cos 2p by p square. So upper limit job is over minus lower limit. So lower limit, x place we have to substitute 1. So we are substituting here 1. So it has become 2 minus 1. 1 into, here also 1, sin p by p. So minus lower limit. So sin p by p. Next, minus, this is problem minus. Here x place 1, cos p by p square. So cos p by p square. Next we are taking the minus sign inside. So minus sin p by p, this minus put together plus cos p by p square. So the entire, the first integral and second integral substitution is completed. The third integral doesn't exist because we know from 2 to infinity, the function is 0. It is given in the, according to our problem condition. Now the simplification here, cos p by p square is written here. The next one, this term cos p by p square. This term minus cos 2p by p square. This term minus 1 by p square. So the leftover is the sin p by p minus sin p by p. They are getting cancelled. Now we can simplify, that is, this put together, both are same similar one. So 2 cos p, this and this put together 2 cos p minus cos 2p minus 1 by p square. So the last step of the previous slide, the more simplification, 2 cos p minus, here in this cos 2a formula, regarding the trigonometric formula, we substituted, that is 2 cos square a minus 1. According to our problem, a is p. So 2 cos square p minus 1, the next to the minus 1 is written as it is, divided by p square. The next step, so we are taking the minus sign inside. So 2 cos p minus 2 cos square p. So minus minus put together plus 1 minus 1 divided by p square. Plus 1 minus 1 getting cancelled. So 2 cos p minus 2 cos square p divided by p square. 2 cos p is common, we have taken outside. So 2 cos p of 1 minus cos p divided by p square is the result we obtained. So we will come to a conclusion of this topic, problems on infinite Fourier transforms. The formula of infinite Fourier transforms, that is, we discussed the Fourier infinite. If x, the range lies between minus infinity to infinity, then it comes under infinite Fourier transform. So the infinite Fourier transform, Fourier cosine transform, it's nothing but 0 to infinity f of x cos px dx. Fourier sine transform, integral 0 to infinity f of x sine px dx. These two we discussed in detail taking the problems. Find the Fourier cosine transform of f of x, the function 1 by 1 plus x square. We have taken, we brought a differential equation format. We solved it with the help, the second part of the problem, that is Fourier sine transform. Instead of applying Fourier sine transform formula from the first formula, what is the result we obtained, from which the simplifications, some substitutions doing, we obtained the result, the Fourier sine transform for the function f of x equal to x by 1 plus x square. The next problem, find Fourier cosine transform of f of x defined by, here 1 should be there, defined by x lies between 0 to 1, the function is x. X lies between 1 to 2, the function is 2 minus x, and x from 2 to infinity, the function is 0. So the three integrals exist here. In the three integrals, first and second integral, first and second integral. We derived it and we solved it. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.